So today we're going to start looking at some word problem applications that are actually practical when we're talking about parabolas and quadratics. So I think one of the most significant applications is that anything that goes up and comes back down follows some sort of a quadratic curve, okay? Whether it's a distance curve, if you think about like shooting a rocket up in the air, you can kind of watch as it kind of goes up and comes back down. That's going to make a parabola, okay? But if you also map height versus time, that's also going to make a parabola because the height of the object, even if it's just going straight up in the air and coming straight back down, you're going to see that as time goes on, the height increases. As it gets to the top, it's going to slow down a little bit. And then as it starts falling again, it's going to start speeding up again. So you're going to see that quadratic show up. So that's what we're going to look at here. So we're going to look at the height of a falling object modeled with this equation, okay, where h is obviously the height of the object. All right, and we're specifically talking in this equation in feet. Okay, and the reason for that is that this negative 16 that's built in, that is the force of gravity on Earth in feet per second. Okay, so the negative 16, that is the force of gravity, right, on Earth. And again, it's in feet per second, possibly feet per second squared. I can never remember which one that is. Okay, so this number would change if you were looking at Mars or the moon or something like that. And obviously it would change if you were looking at meters. I think it's in meters, it's negative 9.8. And it's negative because gravity pulls down. Okay, so you're going to notice we have some direction on here. All right, so that's what that one is. T, in this case, down at the bottom, that's your time. Okay, and it's measured in seconds. All right, and then we have these two guys here. So this one and this one. So the way that you say that zero there, you pronounce that V naught. Okay, so this guy right here, you pronounce it V, and it's not like NAUGHT, which is a fancy word for nothing. Okay, and this one when you'd say H naught. Okay, so that's how you pronounce that. And all that means is V is for velocity. And the fact that there's a little subscript of a zero there is just telling you it's the initial velocity. So it's the velocity at time zero. Okay, so that is your initial velocity. Okay, the subscripts, so that's called a subscript. It doesn't do anything mathematically speaking, it's just a label. Okay, so it's just telling you your velocity at time zero. Similarly, h naught is your height at time zero. So the zero, again, it doesn't do anything, not like an exponent does something. This too does something, right? But these subscripts, they don't do anything, they're just labels. So h naught is your initial height. All right, great. So now that we've got that established, we're ready to tackle some word problems. For right now, we are not going to deal with anything with an initial velocity. We are just dealing with dropped things. Okay, so this one is find the time required for a dropped object to reach the ground from a height of 100 feet and then from a height of 200 feet. Okay, so the question is if it's 100 feet, so it's twice as far up, right? The height is twice as high. So the question is it going to take twice as long for it to reach the ground? So think about that to yourself for a second. Make a guess. Do you think it's going to take twice as long if it's twice as high? All right, let's investigate. So the first one, talking about a height of 100 feet. So I'm going to set up my equation. So the height of my object, okay, is going to be negative 16 because it's dealing with feet. So negative 16 t squared, that's gravity. All right, the fact that we are dropping an object is telling us that our initial velocity is 0. Okay, if it's dropping, it doesn't have an initial force behind it. It's just being let go. Okay, so this would be plus 0t, right? So plus 0t. And then plus our initial height, well, this one we're talking about from 100. Okay, so that's the equation that this is going to follow. Now, we are looking in particular on this particular problem is it's asking us how long is it going to take to reach the ground. Okay, well, reaching the ground, when you hit the ground, I don't know what time that's going to be, but I know that the ground has a height of 0, right? So what this is telling us is it's telling us that our height is going to be 0. And I'm going to plug that into my equation for my initial height, and that's what I'm solving for. I'm going to go ahead and get rid of that 0 because multiplying by 0 is just 0, right? And then this is the equation that we're going to solve. Okay, so subtract the 100 from both sides. Then I'm going to divide both sides by 16. For right now, I'm going to leave that as 100 over 16 because I'm thinking ahead and I'm noticing, well, when I square root both sides, those are both perfect squares. That's going to be convenient for me. Okay, so I'm going to square root both sides and I'm going to get t equals positive or negative 10 over 4, right, which is positive or negative 5 halves. Okay, and in the context of this particular problem, one, when you're talking about time, you're not going to say 5 halves seconds, right? That doesn't make sense. So for this particular problem, you're going to use decimals instead of fractions. Stick with fractions until you get to as far as you can. Okay, but when you get to the end, go ahead and convert that to 2.5 seconds. All right, and even though our answer is positive or negative 2.5 seconds, we know that negative 2.5 seconds doesn't make sense. Okay, that would mean that this object was landing on the ground back in time. So we're going to disregard that. What's actually happening is that we have this parabola and it's like, here's my coordinate plane. This is the parabola that we're showing, that we're modeling here, where this is 100 feet and the object's just starting at 100 feet and then it's going down, right? So this is the intercept that we actually want to have, but there's also an intercept over here. That's what that negative answer was. But in this case, we disregard that as an unnecessary solution. Okay, and that happens a lot when you're looking at practical applications. So for this one, we're going to just say that it would be 2.5 seconds. All right, great. So that's part one. But now we have to look at the second piece, which is what if we did the same thing but from a height of 200 feet? Okay, well, my equation would be height equals, still the force of gravity is the same. All right, we're still dropping it, so it's still going to be 0t for my initial velocity. But now I'm going to have plus 200, my new initial height. All right, I'm still looking for where, oh, wrong color. Still looking for where it hits the ground. That's better. Okay, so that's still going to be a height of 0. So then this is the equation that I'm going to solve. Okay, so subtract the 200 from both sides. All right, and this time when I divide by the negative 16, right, I'm thinking to myself, 200 doesn't perfectly square root, right? But if I divide this one in half, that's going to get me, this will get to 8, and that's not a perfect square. If I divide this one by 4, it'll give me a perfect square. If I divide this one by 4, now that's going to give me 50. So that's not going to work terribly well either. So this isn't just, it's just not going to work out pretty, and that's okay. So I might as well leave it as 200 over 16. Because for this problem, I know that I'm going to use my calculator to figure out a decimal anyway. Okay, so that's going to work out to about 3.5. Again, it's positive or negative 3.5. Get into the habit of making sure you have that. Okay, but then for our final answer, we're going to disregard and say that that's 3.5 seconds. Okay, so to answer the actual question, does it take twice as long? No, it doesn't. It only takes about an additional second to go that extra 100 feet. All right, and that kind of makes sense if you think about it, because once it gets to like terminal velocity, it's going to stay at that speed, right? Versus the speeding up, slowing down aspect. All right, great. Next one. So suppose I hold a biology book out the window. How long does it take to hit the ground if the window is 50 feet above the ground? Okay, so this is going to be similar. I'm going to set up my equation. My height is negative 16 t squared plus my initial velocity is 0 because I'm dropping it. Okay, and I'm starting from a height of 50 feet. I want to know when is it going to hit the ground? Well, that tells me I'm looking for when the height is 0. Okay, so I'm going to plug in 0 here. And then we will solve this equation. So it's going to be 0 equals negative 16 t squared plus 50. So that's negative 50. Right? I have confidence in your ability to solve this. So that'd be 50 over 16. I'm not going to bother to simplify it because I know I'm coming over here and I'm throwing this into my calculator. So it works out to about 1.8. So it takes about 1.8 seconds. Okay, again, it would be positive or negative. I'm disregarding the negative solution because it doesn't make sense in the context of this problem. All right, next one. This one has just a slight variation on it. Okay, we have the same situation going on, but now it's hitting a 5-foot high car. So what that's saying to us is it's saying, all right, in the last problem, when I took a look at my parabola, I was looking for this point right here where it hits the ground. Okay, but now what I'm saying is, well, now there's a car here. It's an awesome car. I know you all wish you could own that car. And it's going to hit here now because it's hitting the car. And I know that this is at a height of 5 because that's how tall the car is. So what I'm looking for now is, instead of looking for a height of 0, I'm looking for, when is this book going to hit a height of 5? Okay, so same setup, right? I know my equation is going to be h equals negative 16 t squared plus 50, because I'm still same situation from here. I'm dropping it out of a 50-foot window. Okay, but the thing that's different is that now it's hitting a 5-foot car, and that's telling me that I'm looking for when h is 5. So I'm going to plug in 5 for my h value instead of 0. Okay, so negative 16 t squared plus 50, and then I'm going to go ahead and solve that. That'll be negative 45. Right? Divide both sides. It'll be 45 over 16. So throw that in my calculator. Works out to about 1.7. Okay. And again, that's positive or negative 1.7. I'm disregarding the negative answer because it doesn't make sense. So it takes up 1.7 seconds. All right. And you can always do just a quick idiot check on these ones to make sure that it makes sense, right? If it's hitting the ground versus hitting a car that's only 5 feet higher than that, it makes sense that the time would be pretty close and that this one would be smaller than that one. Okay. All right, excellent. So that's kind of the new thing. And then this last bit here is just a review for you. So right triangles. Okay, so what we have here is I've got a right triangle, and they tell you that one leg is 5 centimeters. The hypotenuse is 12 centimeters. Remember, the hypotenuse is always opposite the right angle. It's the longest side. The other two are just called legs. Okay, and we want to find the length of the other leg. So hopefully you remember this is a Pythagorean theorem problem where the square of the two legs added together is equal to the square of the final side. Okay, and then we're just going to go ahead and solve that. So I'm squaring each of those, subtract the 25 from both sides, which I can't do in my head under pressure, 119. And then square root both sides. So it would be positive or negative square root of 119. All right, so then if you can simplify square root of 119, do so. 119, I believe, is prime, so that's not going to break down anymore. And again, in this one, we're going to disregard that negative answer as a nonsense answer and just say that our last leg would be the square root of 119. There we go. Fun fact, in the movie The Wizard of Oz, the scarecrow goes after a brain, right? And when he finally gets it near the end of the movie, he spits out the Pythagorean theorem to prove how smart he is. And the funny thing is that he actually says it wrong. So sometime when you're watching that movie, slow that part down and really listen to him when he's saying it.